Okay, well, I'd like to thank everyone who showed up for the early morning first talk. I am going to talk about carbon and water fluxes from Southeast Asian peatlands. And I'm going to focus on a set of what we believe are fundamental insights that we've gained over the last 6 years or so in how this landscape, how these ecological systems function. I'm going to begin with just a brief sort of overview of what peat is, what tropical peat is, and a little overview of our field site. Peat is basically just organic carbon that's accumulated in tropical forests from the detritus of trees, leaves, branches, logs, that don't fully oxidize. So over a long period of time, over thousands of years, this accumulates into deposits of more or less pure organic carbon, which grow in dome-shaped structures, often about 10 kilometers or so in diameter and maybe 10 meters thick in the middle. Let me try this. No. This picture to a hydrologist maybe looks a little bit silly. We see the water table here, and it's actually above the land surface. It's actually true. So one of the aspects of peatlands, one of the aspects of them that enables peat to accumulate is that they're very wet. The water table there's standing water puddles on the surface, and that prevents oxygen from diffusing in so that the organic carbon doesn't degrade, doesn't oxidize. Now, the reasons that we're particularly interested in this are in part practical. Peatlands in Southeast Asia are an enormous source of CO2 to the atmosphere. They swamp fossil fuel burning, certainly from Singapore. And as you all know, it's also the source of the haze, which can more or less close down the region, particularly during El Nino years like this year when it burns. It's also very interesting scientifically. It's the processes by which they form, why they're there, when they're there, aren't well understood. And the ecology of them is different than the other tropical forests which grow on mineral soils and less studied. Here's a map of where we believe they are, and you'll see there's huge amounts of peatland in Sumatra, all around Borneo with a lot in Kalimantan. Singapore kind of sits in the middle of it. In the whole world, this is by far the largest area of tropical peatlands. Now, what's happening to these peatlands, almost all the forests have been cut down and they're being drained. And as a result of that, it's oxidizing and subsiding. This is a map of some recent results that we've obtained by analyzing the Japanese LiDAR satellite, the ALOS satellite. And we've been able to map out this rate of subsidence. It's quite dramatic, on the order of 5 centimeters a year or so. Since the peat surface is often only a couple meters above sea level, this means that large areas of land will disappear below sea level in 50 or 60 years, displacing people that live there. And if we extrapolate this over the whole region, we can get the total carbon flux. We haven't done that yet. But others have done that, and they get a CO2 emissions per year on the order of a gigaton per year or so, which is huge. The emissions from fossil fuel burning in the US is on the order of 5 gigatons per year. And of course they burn. This is just a cell phone video from near our site. And they burn in a way that's dramatically different than other forests. It's a very low temperature burn. In fact, the trees and vegetation don't burn above the peat often, so you can't even see it with remote sensing methods. When this happens, there's enormous emissions of carbon. It's been estimated in the last big El Nino, emissions of carbon which are in fact larger than fossil fuel burning by the US or by China. Okay, to understand how these ecological systems work, we spent a lot of time establishing a field site where we can actually put in sensors and instrumentation to see what happens when they're wet, when they're dry, and over the long term, how they grow. We picked the country of Brunei, in large part because it has what we think might be the last pristine tropical peat forest on Earth, in fact. And here we're zooming into the area where our field site is. This is the border with Malaysia. You see the forest has all been destroyed on that side, but in Brunei it still exists. Zooming in a little further, you can see overviews of the two sites that we've heavily instrumented. One that's deforested with just a few remaining large trees, and this pristine peat dome here, which has 50-meter trees uniformly covering the whole area. Now, we've put a lot of effort into building the infrastructure, including towers and lots of instrumentation. These sites are completely off the grid. There's no access by road, there's no water, there's no power, and I guess shockingly to the students, there's not even cell phone coverage. So it's a large effort to get in there and get all of this instrumentation working. Now, if we stand at the top of one of the towers and look out, we can see this canopy of huge trees, 50-meter high trees. Here we're 15 meters above the top of the trees. If we go down below, we see there's almost a second forest, a very diverse forest of smaller 25, 30-meter trees. And come down to the forest floor, you see this lots of roots, buttresses of trees, fallen trees, and that kind of thing. And if we look straight down at our feet, we see water. So standing water in lots of places. Okay, now our research has focused really in four areas. And today I'm just going to talk about this sort of fundamental question of how do peatlands exist, what makes them disappear, what makes them grow. I want to mention, and for those of you in the SAB, I'll try and hit this when I talk to you again tomorrow, two other aspects of the research. One is micrometeorological measurements in the atmosphere of fluxes to and from the peat. Another is geochemistry, particularly with a focus on methane production and consumption in the peat. And lastly, forest ecology, which Alex is going to talk about right after my talk. So the fundamental question can be put as sort of a chicken and egg paradox. How is it possible for peat to grow when the only way it can grow is if it already exists to confine the water that enables it to grow? And that's what I'm going to try and unravel through a set of data that I'm going to work through. Another kind of insight that helps in our thinking about it is to realize that if we understand the dynamics of the peatlands, then we necessarily understand the carbon fluxes. Because the peat's completely made up of carbon, as the land surface shifts, those represent fluxes in and out of the peat of carbon. Okay, and the way I'm going to do this is I'm going to quickly present four different empirical findings, and then I'm going to try and tie those together to give an overall understanding of the functioning of this landscape. The first finding is sort of a geologic finding, and that is that as peat grows over thousands of years, it grows up in layers as pancakes. A second finding is that the surface, the topography of the peat, has a uniform curvature. And what I mean specifically by that is that the Laplacian, the sum of the orthogonal second derivatives of the elevation, have the same value everywhere. So there's this one parameter that describes the shape of the landscape. The third is I'm kind of moving down in scale and moving down in scale in time also is what a hydrologist might observe, and that is that the water table moves up and down throughout the entire landscape in exactly the same way, and from rainstorm to rainstorm in the same way. So if we have one kind of universal curve of water table elevation, we can always follow that to see what it'll do next until it rains again and jumps back up. The water table jumps back up and then follows it again. And the third is that the rate of CO2 emissions from the peatlands is a simple linear function of the depth of the water table. So when the water table is above the surface, there's little emissions, and then the emissions increase as the water table rises. Now, what I'm going to do is kind of work through these in reverse order, from the simplest thing, what a biogeochemist would focus on, to the sort of larger scale thing, what a hydrologist would focus on, then to what a geomorphologist would focus on, and finally to sort of what a geologist would focus on to tie it all together. So here's one of these sort of robotic things that we have out there that measures carbon fluxes. And the basic idea of using these is that as the water table moves up and down in this narrow vadose zone at the top of the peat, the emissions change. The emissions of CO2 change. And by putting this out there, we can measure both of these things and come up with this relationship, which I already kind of summarized, where as the water table falls below the surface, the emissions of CO2 increase linearly. Okay, so still moving backwards, this notion that the hydrograph is universal. What we did here is we just put in lots of wells with pressure transducers and then measured this hydrograph across the landscape, also measured the rainfall. And here's rainfall, flow down tree trunks. And if we look at just one little piece of data, what we see is every time it rains, it jumps up, and then it falls off with a diurnal wiggle in there from day to night. Now, if we take this and sort of chop it up, remove the rainfall events, and slide all these guys over, then we can get that, what I'm calling a universal hydrograph. And we can also keep the rainstorm events and see how they jump up from place to place and time to time. So we do that, put it together, we can come up with how the water table increases as a function of the depth of a rainstorm event, and then this hydrograph falling off like that. And the point that's exciting to hydrologists here is it's more or less the same at all times, at all places, except for one kind of outlier here. When I used to give this talk, I used to sort of wave my hands around and say, oh, well, you always have an outlier. I'm going to come back to this and actually use this outlier as sort of the proof of the overall concept. I'm kind of excited about that. Okay, so working back further, the peat has a constant Laplacian. Now, what this means is that the landscape has this curvature, which is uniform everywhere, and we were able to study that by both sort of traditional methods of simply surveying it and also airborne LiDAR to map it out. Here's a picture of the dome with our tower sitting right there, and with that LiDAR, we're able to map it out. And sure enough, it seems to work out pretty well, that the curvature is the same almost everywhere. Now, let me mention I don't have time to go into all the mathematics here, but I want to mention just a couple sort of underlying things that lead to this derivation. One is that if the water table is going up and down uniformly everywhere, then the carbon flux is necessarily uniform everywhere, right? Because it's just the exposure of peat that controls the carbon flux. The second point is that we didn't sort of discover that Laplacian is uniform everywhere. We predicted, in this case, we predicted it and then verified it. And the way we predicted it was we said, well, under what circumstance is it possible for the water table to move uniformly up and down everywhere? And then working through something called the Boussinesq equation, you predict that the way that would happen is if the surface has a uniform Laplacian. Okay, so what does it really mean, uniform Laplacian, in the simplest sense? Well, it basically means that wherever you have an indent or you have less curvature than other places, that's going to be a wet place so that peat will accumulate there. And wherever you have a very large value, a high curvature, that's going to be a mound or a bump, so peat's going to oxidize and disappear there. So over time, this will fill in, that'll go away, and you'll come to something. In this case, it looks like a parabola, and that has this characteristic of uniform carbon emissions across the landscape. Now, we can do this gives us some really basic insights that I think are really useful. This is the Laplacian, which is uniform, and we actually know what it is. We can calculate it from this kind of complicated statistic, the mean rainfall rate over the mean transmissivity, where the transmissivity is a function of how the water table moves. Now, the amount of carbon stored in a peatland is proportional to the Laplacian. So we can ask questions like, well, how much carbon would be stored if rainfall were to increase? Or how much carbon would be stored if seasonality were to increase? These are both things that are predicted by climate models. And we can come up with graphs like this that show us the total carbon storage across the area as a function of the mean rain and also the interstorm arrival time, which affects this mean transmissivity. Or the amount, here's where we stand right now and what we believe the annual variations in rainfall are and what the ENSO amplitudes are. And this is a kind of rough prediction by climate models of where we're going to go. So the prediction is we'll lose about a third of the carbon over the long term if these climate models turn out to be correct. Okay, so the final result is that peat grows as pancakes. And the way we found this, the way we verified this, is by taking lots of cores and carbon dating the peat. And in that way, we can map out a three-dimensional structure of the paleosurface of the peat over the last 3,000 years as it's accumulated. Now, previous sort of theoretical models have predicted that peat might grow like this, from a little bump radiating out, or it might grow like this. If we take the understanding that I've described so far and predict how it would grow, we get something like this. It grows up as sort of pancakes stacking on top of each other, or the way I like to think of it is something familiar to many of us. It looks something like that. Now, let me return back to this outlier. So the concept of the uniform Laplacian is a steady state. That's the equilibrium you reach if nothing changes. But this concept of peat growing as pancakes is a dynamic model. That describes how it grows over time. And it can also be used to predict how it'll disappear over time if climate changes. So what's this thing right here? Well, this is on the inside of the dome, where we believe the peat is still growing. And sure enough, what this is showing, this well, this piezometer that's furthest into the dome, is wet. It's not a lot wetter, maybe just a couple centimeters, but that's enough to shift the balance there from an equilibrium where the carbon input and output are balanced to one where it's wet enough that carbon's actually accumulating, and that final pancake in the middle of the dome is in fact still growing there. Okay, so with this model, we can predict the future, but we can also try and understand how the landscape got to be where it is now. And to do that, we have to have an understanding of what the paleoclimate was, what the rainfall was in the past that controlled the growth of peat. So other people have gone to nearby caves here and from stalactites measured the oxygen isotope ratios, and we have a basic idea of how rainfall has changed over the last 3,000 years. If we put that into our model of peatland dynamics, we're able to predict what the ages of peat would be in the past. So what this plot shows is our model predictions of this layered growth of peat and measurements from carbon dates from a variety of cores. And it seems to agree pretty well. So to sort of finish this up, what I've done here is to try and give you, without the mathematics and a lot of details, an overview of this sort of model, this basic conceptual understanding of how tropical peat forests grow. And I think the model is nicely verified by a number of very different types of data. One is that we predict that the water table dynamics are uniform. The other is that the topography has a uniform Laplacian. And the third is that the radiocarbon dates are consistent with the model prediction of the peat in the past. Now, we have one adjustable parameter in the model, and that's the rate at which new organic carbon rains down and accumulates. We have to adjust that in order to get the right height of the peat dome. But all three of these observations that verify the model are qualitative. These aren't matters of adjusting parameters. These are sort of basic features which the model will always require, will always predict, regardless of what the specific parameters are. So the last thing I'll talk about is just to give you a quick example of the kinds of things we could do with this model. Let me say that the reason we're kind of excited about this is that this is now a tool that will enable us to do a lot of things. With this understanding, we can come up with ideas on how you could regrow, regenerate peat forests now that we understand how they operate. We can come up with predictions of where fires will occur, because whether the peat is flammable or not entirely depends on the depth of the water table. With this understanding of how the water table behaves, and particularly with things like the ALOS satellite mapping, we can actually come up with reasonable, I think probably very good models of where peatlands are flammable and hence where fires will be. We can also come up with engineered solutions to reduce the drainage of the peat. Right? We understand how water moves through the peat. We understand how the water table behaves. So we can come up with solutions to peat flammability. But what I'll show here is some simple calculations for sort of an idealized peat dome as to what we think will happen in the future if we do nothing. Two things will actually increase the amount of peat in Southeast Asia, lead to more carbon sequestration. One is that if the predictions are right, of more rain, we'll get a slight increase in the elevation or the amount of peat. The other is if sea level rises by, say, here, a meter, then the peatlands simply grow up. Both of those things sequester peat. However, two other things we would predict will lead to less peat. One is increased seasonality, so dry summers are going to cut it way down. But the fundamental result that's just almost sort of painfully simple here is that all of these things are completely swamped by the drainage of peat, which is now occurring everywhere. So unless that's stopped, all the peat we can pretty confidently predict will collapse and disappear. So I better stop there. There's a whole team of people who have worked on this, and I'm sorry I won't go through all of them, but you will meet one key figure next, Alex Cobb. Thank you.
Can we take some questions?
Oh, I got time?
Yes.
Oh, I thought
A couple of
I was way
questions.
out of time. Okay.
No. Questions, please.
Is there any prospect for engineering peat domes using this new understanding for deliberately sequestering carbon? And to what extent does these effects you described in the last slide sort of stabilize or amplify climate change in terms of CO2 in the atmosphere?
Yeah, I think there are ways to engineer peat domes to start sequestering carbon. But sort of the first thing is sort of silly thing is that it's much easier to engineer them to stop emitting carbon, and that's you get much more for your investment on that. But over the long term, I think that could be done. And it's simple things like that fire that I showed burning. That was near our field site on a road, and the reason it's burning, I think, is that whenever roads are constructed there, they're drained just to keep the road from flooding. And now you get all these fires within the first couple hundred meters of either side of the road because the peat's dry there. The same thing is happening across palm oil plantations across the area. So if you engineered that a little bit differently, you could prevent those fires. What was your second question? Okay.
Yes, sir. One more.
Charlie, the hydrograph has a diurnal component.
Yeah.
I get the impression that there was a small amount of nighttime recovery.
Oh boy, Harry, you zoomed in on a fine detail that we spent too much time thinking about. So for the rest of you, you might expect it to be flat at night because transpiration turns off. And during the day, that whole drop is just evapotranspiration from the trees. Or you might have expected to decline a little bit because there's groundwater flow through the peat and it's going down. So why would it go up a little bit? One answer is that it's wrong. There's huge barometric shifts from day to night, so we have to be very careful to account for that. Another possibility is dew. Do you have a third one?
No, I'm wondering.
Okay, yeah.
One more. Okay, thank you, Charlie.
Thank you.